Okay. Here we are. So I looked into the homework problem 5 and 6, and a couple of you guys or more, I did not yet see your homework assigned. So basically, from now on, your midterm exam will be based on these homework that you do. And it's better working on this because specifically the homework following this week will be considered as your exam, midterm exam. So work on them. It has the value in learning of these subjects, and it has the value for your exam. One of the things I noticed that quite a number of you guys did not work through was the problem number 5 and 6. I provided you with a solution, but I would like to refer that here again. And we discussed the case. Hold on a second, my pen didn't write correctly. We did this and a straight line here. We were talking of the cantilever beam, and I don't remember which direction was fixed, which side was fixed, but there was some sort of linear distributed load was applied. And in this case, we gave you the stress function, which is a polynomial. And any, as we learned before, any cantilever beam or straight beam or any type of a beam can be formulated by these polynomial function. The other way is using Fourier series, but let us stick to that polynomial function. So the phi function is given. From phi function, all of you could calculate the stress function. You're just getting the derivatives appropriately. You arrive at the stresses, but that's not the end of the story. These are the stresses that come with some constants, and they would satisfy with all the constants possible the elasticity equation. Is this the solution of this problem? How do you know? How can you be sure this is the solution of the problem? And that is the next part that you miss. You just stop. Stress is given as a function of all those constants and stop. That's not the end of the story. We need to show that these stresses would satisfy the boundary condition as indicated here. So what are these boundary conditions? That's important. That's the major task. We're getting the derivative, and that you can feed it into computer and it gives you the answer. We are more than a computer. We are human. We have a brain to use. So what is the question here? Is the boundary condition. It's very difficult to set up this boundary condition for a computer program, but you can work it out easily. This is a beam. It has 4 faces, generally speaking: up, bottom, left, right. Right-hand side is fixed. Left-hand side is free. So what should I write here? First, look on the upper and lower side. These should satisfy exactly per stress distribution given, as we discussed. Looking at an element on the top, enlarge that element. On any element, I will have sigma x sigma y and shear stresses tau xy for a two-dimensional problem. These stresses at the boundary, at this elemental boundary, should match external forces. Do I have shear here on this top? No. So the shear stress tau xy, if the thickness of the beam, I believe, was 2c, and the axis was at the middle, central axis of the cross-section of the beam. So at c, at y equal to, if y positive in your textbook is shown at the bottom, and this side is x. So y equal to plus c and y equal to minus c, I don't see any shear stress here and there. So the shear stress tau xy should be equal to 0. So in the equation that you define shear stress with some constant, make that shear stress 0. You have two relationships that needs to be satisfied on the top and the bottom so that the shear stress will be 0. That's one thing. In the bottom, sigma y as well should be 0 because there is no force balancing that sigma y on this structure. So sigma y should be equal to 0 at y equal to c. What about sigma x? Sigma x is not on the boundary. Sigma x is on this face, and that face is not on the boundary. This face is on the boundary. This face is on the boundary. So I don't worry about sigma. On the top, a distributed load is applied. So if I consider an element here, the sigma y here should match this external load here. So if this is my triangular stress, what is the intensity of the load at the distance, say, x from this side? So what is this actual, if I call it B and call this A, in this triangle, and at this distance is x, you can write the similarity of these triangles, the larger and smaller one, and say B over A is equal to, if the total length is L, L over, I'm sorry, L minus X over L. So you can calculate what is B, which is intensity of the load there, and that should match sigma y. So your sigma y should equal to B. Make that equal, write that equation, you get additional equation. So the upper and lower boundary are satisfied as such. What about left and right? The left-hand side is free. So there is no shear load here. And there is no axial load here. And there is no moment here. So I should show that the sum of the stresses, sigma x, is dA over the surface area should be equal to 0. Sum of the shear stresses tau xy, dA, should be equal to 0 for integral, or integral of sigma x times y, which is the moment of that stress with respect to the neutral axis, should be equal to m. Oh, and m is 0 should be equal to 0. This is the way we satisfy the boundary conditions at the two ends of the beam. If there was a shear at the end, that integration should give you the shear. If nothing, it is 0. If there was an axial load here at the end, P, it should be equal to P. If not, it is equal to 0. If there is a moment here at the end, it is equal to moment. If not, it is equal to 0. These are the boundary conditions based on the forces and stresses that we need to satisfy. We need to satisfy these, otherwise, the solution we obtain satisfies elasticity equation, but it's not the solution of my problem. The next thing, of course, goes into part C, and it would be displacement. At the end, it is fixed. How do I satisfy that boundary condition? How do I know that this is this solution of my problem that satisfies this end solution? As we have seen and talked about this many, many times, at the end here, not all the points can be fixed. We fix as many points, as little as many points, such that rigid body motion of this beam is prevented, not more. So at the center line here, at this point, I say I cannot move vertically and I cannot move axially. So U should be equal to 0, U should be equal to 0, and V should be equal to 0. For U in this direction and V in the other. So at that point, it is fixed. This point cannot move up, it cannot move down. But still the beam could hinge about that point. So I need to fix the rotation. How do I fix the rotation? In the usual formulation in mechanics of material, we assume that the slope here at this end is 0. But in reality, I can make slope in this plane equal to 0, or the slope at this end is equal to 0. The vertical or the horizontal. Derivative of V with respect to x is equal to 0, U with respect to y. So both of them is feasible assumptions, and we arrive at two different solutions. So we have to satisfy these boundary conditions. And how do I do that? Once the stresses are calculated, I use the Hooke's law to calculate epsilon x, epsilon y, and epsilon z, and gamma xy. I'm sorry, there is no third direction. Gamma x, these three strains from Hooke's law. Once the stresses are known. Once I calculate the strain, I know epsilon x derivative of u with respect to x, epsilon y derivative of v with respect to y, and similar, a gamma xy derivative of u with respect to y plus derivative of x with respect to u with respect to x. Integrate the first equation, you get u. But it will be a function, it has a constant, which is a function of, because we are getting derivative with respect to x, it should have a function of y. Getting the derivative of integral of the second equation, you would have another function which would be another constant, which would be a function of variable x. Substitute u and v in the third equation, you get a relationship between gx and fy, and that expression for every value of x and y should be equal to 0, from which you should be able to calculate the function fx and fy. And at the end, you end up with the equations for the displacement, which has at least 3 constants. Constants, not a constant, a function of variable, 3 constants. This is as far as the integration of displacement goes. Now, the next step is to satisfy rigid body motion, as I mentioned. Make the end equal to 0. Make at x equal to 0, y equal to 0, v and u should be equal to 0. That's 2 equations. Make the slope here equal to 0. That would be third equation. And with this third equation, all these 3 constants can be calculated. And you have fully defined problem that would satisfy the displacement boundary condition and would satisfy the stress and force boundary condition. This is a story with the Cartesian coordinate system and these beams. When we were talking of disks and circular axisymmetrical bodies, we indicated that there is another type of boundary condition that comes into the picture. And that is to say that the solution should be single value. That is to say, if I have a disk and I calculate stress for theta equal to 0, at that point, when I turn 360 and I put in my equation 360 degrees for theta, I should not get a new value. I should not have multi-value, infinite number value for the same point on the object. These are boundary conditions. That is, in a sense, that what I would like you to remember and learn. William is coming in. William, you're in. And this time I miss Marco, Jonathan, and Albo. Hopefully you were doing something more valuable than attending the class, William, that took you longer time to join us. Hold on a second. All right. Let us now work on that problem. I have the solution provided for you, but work on that problem and be sure that you can work that problem independently. You can satisfy all the boundary conditions, you can satisfy all the displacement and arrive at the correct solution. Go back and correct that problems. If you do so, you can resubmit and I reevaluate your homework. Right.
Professor, you said we can resubmit our last homework?
Yes, yes.
Okay, thank you.
So basically, my aim is not here to test you guys. That's not the aim of the university. That's not what we are intending. It's not testing institute. It's learning institute. We want to transfer knowledge from one generation to younger generation and we don't want to lose those information. Well, that story goes when we were working for Boeing, and some people initially, say, who knows, 30, 40, 50 years ago, worked on these satellites. They developed many complex formulation for the survivability of the satellite, for the effective environment on that, the testing needed to be assuring. So a lot of these things. And those information were gathered and placed in all the paperwork and drawings. And some of that, unfortunately, were just in position of the of those people who made initial design and formulation of the product. We don't live forever. So those people retired and out of picture, and the same unit, the same component was being used again on this similar structure, and an engineer replacing the previous design. Now, he gathered the information, studied the case, what are the paperwork, it's tons of information. Some information were lost, unfortunately, because of bad recording at that time. So when we went asking these experts in that particular unit or the components, why we are doing this test, for example, what's the benefit of running this test on this component, which is costing us, say, millions of dollars. It was dictated by the previous designer to do that test, but the new engineer had no answer for it. He didn't know why. He said, it's written in this document to do this test, but he didn't know why to do this test. So when they were asked, can we omit this test, he had no answer for it because he didn't know the source of requirement of that test. It wasn't recorded. That's the problem that we don't want to miss here. We don't want knowledge and information be lost. So that's the attempt here, to transfer as much information as possible to you guys, so you can pick it up from the time that we left and progress, go further. My hope is that at the end of this session, you know better and more of theory of elasticity than what I know. That's the way to progress. If you know less, that means every new generation would know less and less and less. That is in the opposite direction. It doesn't work that way. It happened with that test. We noticed later on, which was redundant, and it was done for the type of a rocket that was being launched at that time, and it was the requirement of that rocket for the new rocket design of 50 years later. That test was redundant. So that's the point here. Now, let us concentrate on what we have here at this time. Now, I just waited so that a couple of other guys could join us.
Excuse me, Professor.
Good evening.
I have a quick question.
Is that who is that? Is it Marco who just joined? Who just joined? Carlos.
Yes, that's me, Professor.
Oh, you were in before.
I'm sorry?
You were in, you just left and come back?
Oh, no, I'm just showing up right now.
Oh, somebody just joined the
Yeah.
session.
I just joined. Yeah.
Is that who is that? Carlos?
Yes, sir. It's Carlos.
Okay, I just wanted to get the record here. So at this time, still I am missing Alba and Jonathan and Marco, and they are not yet in. Okay,
Excuse me, Professor, I have a quick question.
yeah, go ahead.
The corrections to the homework, when are they due?
At any time,
Okay,
you can find time, make a correction, and we look into that.
okay, thank you, Professor.
Again, my aim is that for you guys to give the opportunity to learn as much as possible. It's a very complex thing. Theoretically, mathematically, it is very demanding subject, this theory of elasticity. And if you really master this science, you will be really an expert in this field of structural analysis. You won't be only copying work. You can develop the theory, and if you are interested in research work. Now, one of the common problems we have, and we did not that well address in mechanics of material, is that what happens if I have a beam and a concentrated load P is applied on that beam? A sharp concentrated load applied on that beam. We generally say in the vicinity where the load is applied, we have a large disturbation of the stress field. We don't know how it is. What are the governing equations for that? So we say we go away few lengths or thicknesses away from the load applied, and say the common equation for bending of the beam would work there, but we don't know what happens here above. So we just remove it from our analysis. This is what we want to address now. We have the load P applied in this example on an infinitely thick plate. So assume is this surface here of the ground surface is infinitely thick. So we have all the material underneath, and a load is applied here, a concentrated load applied. So consider an elastic continuum of semi-infinite body where a concentrated load is applied. The problem is a two-dimensional problem, so we don't look into the thickness. But for the sake of understanding of how it works, this concentrated load applied here, it means a uniformly distributed load through the thickness as shown. So this is the type of the load applied, and assume in formulation of the problem that the thickness is equal to 1 unit. Or better, we can say the thickness is constant. Two-dimensional problem. So basically, as you can see in this picture, a concentrated force is applied on this elastic body, and we want to see what would be the distribution of the load. A lot of research work has been done on this problem. It's important many cases we have these concentrated load applied on the body, and we want to see what will be the effect of it. Let us draw a circle as shown here. Can I move that circle? Yep, I did it. Let us have a circle of diameter d, as you can see in this picture. And let us consider an element, a polar element on this on the circumference of this circle. And that is my polar element. Well, I don't think I can. Let me delete this. Draw. An element here. Let me choose a different color. So I draw. Consider this element here, a polar element on the circumference of this circle, and it is at the distance, polar distance r, coordinates of this, use a different color, coordinate of this element is defined by the radius r and the angle theta. So a polar element on the circumference of this circle of diameter d is selected. What we say that all the elements on this circle, every point on this circle would have a zero shear stress and zero tangential stress, and only has a radial stress, which is defined by this equation. So the shears, the sigma theta is zero, and shear on the faces would be zero. And only I have sigma r, which will change with angle theta. If theta is equal to zero, that is, I am on the x-axis, sigma r would be maximum 2p over pi over r. So for theta equal to zero, the stress would be minus 2p over r pi r. As the theta increases, the stress decreases according to the cosine law. And when theta equal to 90 degrees, when I am on the top surface, sigma r is equal to zero. So on this top surface, this side or that side, sigma r is equal to zero. If it wasn't the solution of my problem here. The boundary condition says I should have no load on this surface and no load on that surface. It is a function of reciprocal of r. So as r goes to zero, that means at this location, sigma r is infinite. So you can see sigma r does not exist anywhere except when r is equal to zero. which goes infinite. And that is defining the singularity of the concentrated load at point O. That's what we expect. Just under point O, the stress should be infinity, and anywhere away from that is defined from this equation. And you can see you increase the value of the radial direction, the stress decreases. So as we go further down onto this plate, the stress through the thickness of this plate, the effect of the concentrated load would diminish. Now, why is it a solution? Why and where did I get that solution from? Somebody made that solution available to us through his research work, trial and error, back and forth. But the solution is given to you, assume, and we are asked to check if this is a correct solution. If this is satisfying the elasticity equation, and also it satisfies the boundary condition. The boundary condition I've shown easily here that it is satisfied. I don't have any stress on OB or OA except immediately under the load. That becomes infinity, and that is the way the problem is represented. But I have to show these stresses also satisfy the equilibrium condition and also the compatibility equation. If that is shown, it would be the true stress for this problem. From that stress distribution, I define an area function, minus P pi r theta sine theta. Now we work reverse and see if an area function of that form would give us, first of all, the same stresses that we indicated, and secondly, it would satisfy the compatibility equation. Because if the stress, if you remember, is defined by area function, I don't need to satisfy the equilibrium condition. I could have worked out and say these stresses would satisfy the equilibrium and work through the equilibrium equation in polar coordinate system and verify that these are satisfied. But let us, as it is indicated in your textbook, define first the area function and notice the derivative of area function with respect to r divided by r plus 1 over r2 derivative of area function with respect to theta twice would give you sigma r. So work through that problem, get the derivative with respect to r and theta, simplify. You would see the same stress that we defined in the previous slide is obtained. Derivative of phi with respect to r twice, it is of r into power 1, so second derivative would be equal to 0. Shear is defined by this expression in polar coordinate system. Get the derivatives accordingly, simplify, you would see that the shear stress is 0. So the area function that I defined on the top would give me the same stresses. So we can begin from that. I don't need to satisfy now the equilibrium equation because the stresses are derived from this area function. But I need to satisfy the compatibility equation. it is not that difficult to substitute for phi, p over pi, r theta sine theta in this equation. Get the derivative with respect to r twice, derivative with respect to r, derivative with respect to theta square, add them up, and then again, get the derivative with respect to r twice, get the derivative as shown here, and at the end of the day, show it is equal to 0. I did not show the detail, it's just a simple math. So we satisfy the case for the compatibility. The stresses are derived from equilibrium from the area function, so elastic. This is a true solution for for some problem. Is it exactly the solution of my problem? I can see that the boundary condition are satisfied or not. At along the straight boundary of the surface, when theta is equal to 0 or 180 degrees, I'm sorry, 90 or minus 90. Let me go back to this picture. When theta equal to, let me get my pen. The theta here is 90 degrees or minus degrees to get that surface and that surface. Either case, plus minus 90 degrees, plus minus pi over 2, sigma r, cosine of plus minus pi over 2, 90 degrees is 0. Therefore, sigma r is 0. And therefore, this says the stress function that we define would satisfy my boundary condition. I'm sorry, I was talking of sigma theta, not sigma. So we have to be careful when we are talking of the boundary. Always draw the picture. I'm talking of this element here on this boundary. At the top, I don't have the stress. On these two sides, I have the stress. And it is a polar coordinate system. So as I turn around here, this is the direction of sigma r. So this is the direction of sigma r, and sigma r is within the material. So all I need is to show sigma theta is 0. And it is actually 0 anyway, and that's it. So now, the next thing is to show that this force is balanced by the stresses that are generated in the system. Where is my equation? Okay, here we go. So let me draw the picture. This is where the load is applied, and I consider a circular boundary under that load. So the load is applied at the center of the circle, and let me bring Chris Tucker. Yes, you are back. Let me draw a better picture. I wish we had the blackboard and we would work much easier there than using the mouse and trying these things. So this is the load applied here. And this is my semi-infinite body. And I cut a circular, as you can see, a circular thing here and I study equilibrium of this semi-cylindrical body cut from the material with the external force. So this is external force, and on that circumference of that circle, we have all the radial stresses applied. This is sigma r. And sigma r is defined by that expression. At the constant radius r, when r is constant, the sigma r would be a function of theta. And it would be maximum on the vertical direction. And as we go to the edges, it gradually dies out. So some of these stresses applied on this surface should balance the external force P. That is to say, sigma r for each element times the effective surface area, which if you consider an element here, where this angle is d theta, this is radius r. Projection of sigma r on this element would be sigma r times r cosine theta. If we integrate that, it would be equal to force minus 2. So, in fact, the solution we have would be in equilibrium with the external forces that generate it. Are we fine? Any question at this time? Do we understand what we are doing? I select a small element on this circle. If that radius is r, this angle is theta, d theta. What is the length of this arc? R d theta. What is the thickness of this plate? We said it is unity, right? The semi-infinite body that we considered had a thickness of 1. So the area would be, in fact, r d theta. Times sigma r would be the total radial force applied on that element. But that radial force, it is at an angle theta. Projection of that radial force in vertical direction would be sigma r cosine theta. That is for this element. If I integrate from the beginning of this cylinder, semi-cylinder, to the end, it gives the total force in vertical direction. And it's shown to be minus 2.
Why is the upper bound only half of the semicircle?
This is the problem. I have semi-infinite body where the load is applied here. That's the beginning, right? So I'm cutting a circle from this body, half a circle from that body. It would be separated, right? Do you follow?
Yeah, but isn't that 0 to pi, not 0 to pi over 2?
Is if I change my, this is where the angle is changed, right? This is theta, right? It changes from say pi over 2 to 0 to minus pi over 2, right? But because of symmetry, that would be equal to 0 to pi over 2 times 2.
Okay, yeah, I get it. Sorry.
Okay. Yeah,
Thank you.
it's good to see the details there. When I'm reading that, I may forget all the details. That's a good question. I can also, it's not indicated here directly, but for the sake of your curiosity, let me clear the picture here. You can also show that these are the forces up right here, right? And we project it along this axis, and the total force was shown to be P. But projection in horizontal direction, what would be the case here? You would see because of symmetry, this horizontal force cancels that horizontal force. So if you integrate the projection along the x-axis from here to here, should be equal to 0. Of course, because of symmetry, this is obvious, but you can test it. Get this one times sine theta and integrate it in a similar fashion. You'll see that it's equal to 0. So we are satisfying the boundary condition. We are satisfying the elasticity equation. So that is the solution we have. And remember in the beginning, I say, consider a cylinder of the radius or diameter d there. If you go, consider that stress distribution as we indicated here, sigma r given by that equation, and calculate the stresses on this circle of diameter d, you would see that the stress would remain constant. Stress would be minus 2p over pi d for any element on this circle with the diameter d, or any element on the circumference of this circle. Stress, radial stress is constant. So that is what you can imagine what would happen. If a concentrated load is applied at that point, we generate stresses that keep decreasing if a larger circle are selected. On this circle, on that circle, on that circle. And as the circle becomes smaller and smaller, the stress, radial stresses are larger. So it propagates in the form of these circles that I have drawn. The larger the circle, the smaller the stresses. So the further away you go from that point of concentrated load, the smaller the stresses will be. And you can see the picture there. If you can test this solution by photoelasticity, and you can see that the pattern developed there would show the stress is reducing according to some picture here. So if that stress level is shown with certain color, here we have red, then on this circle we have pink, and then it grows to probably blue at the larger circles. The other thing of interest is that we obtain these results for in terms of polar coordinate system. Now, the next thing of interest is to calculate stresses on this segment, on this line, which is at the distance A from the top surface. I want to see at the depth of A, what would be the effective stresses on this semi-infinite body along this line. So this is sigma, this is my y and x axis. I want to convert it to polar coordinates sigma r and sigma theta, or sigma r and sigma theta. So r theta is given. I want to calculate sigma x, sigma y, and tau xy. The transformation is simple rotation by the angle of theta. So sigma x, sigma y, and tau xy by simple rotation of theta. If you use the transformation formulation that we were made familiar with, are given by this equation. Remember, we have only sigma r, sigma theta and tau theta are 0. That's why the transformation formulation is this symbol. But these sigma x, sigma y, and tau xy are given in terms of sigma r and theta. We want to calculate them in terms of the Cartesian coordinate system, in terms of x and y, rather than r and theta. So what do we do here? Substitute sigma r here, which is 2 pi over pi cosine theta over r, times another cosine theta. So you have this term. And notice that this is my y, a that it is shown here is my x at that location. So x is equal to r cosine theta in polar coordinate system. So substitute for x, which is a here, r cosine theta, or substitute for r, x over cosine theta, you end up with this equation. And similarly with the other two equations. But still, these equations are expressed in terms of the distance a and angle theta. I can further calculate what is cosine theta in terms of the angles, in terms of x and y. Cosine theta is x, because r cosine theta is equal to x, r sine theta is equal to y. So if we square it, r2 cosine 2 theta is equal to x squared, and r2 sine 2 theta is equal to y squared. So you can say, can add them up. And of course, r2 would be x2 plus y2 squared. And cosine into power 4 theta would be this into power 4. So it would be x into power 4 divided by r into power 4, and you can work it out. R into power 4 would be x squared plus y squared into power 2, and you end up with this equation. I have one x here, cancels with x4, so it becomes x3. Eventually, these three equations gives you sigma x, sigma y, tau xy in terms of the Cartesian coordinate system x and y. In particular, I am interested to see the stress at the depth A. So when the x is equal to A. So we want to see what would be the sigma x when x is equal to A. We can put it into that equation. To better realize the variation, probably we best is to get the graph of the stress variation along the line MN. You can see at the depth D here, the maximum stress as we would expect it at this location. The maximum radial stress would be just under the load. And as we go away, it gradually reduces and becomes smaller and smaller as we go away from that. So the curve on the top here shows the stress distribution of sigma R along MN. If you look into the sigma theta from this equation, you can see the variation of sigma theta according to this graph at the bottom. So sigma theta at the bottom here, when theta is equal to 0, I have sine theta equal to 0, right? This would be 0. And similarly, shear stress would be 0. But sigma y and tau xy also away from the load would tend to 0. So somewhere in between, it maximizes. That shows the variation. This is the case of one concentrated load applied at a point on your surface. Now, if the concentrated load was applied at this location, at the distance O1, the stress underneath of this P1 would be similar to this picture. But the stress due to P under the force P1 would be this one. So stress due to P under the load P1 is this one. Under the load P2, it would be this one. Now, I can add them up. What would be the stress at different location if all these loads are applied simultaneously at different points? If the load P is applied, the stress under that load is defined by D1. P1 is applied because it's at the distance as shown here. The effective stress due to P1 at this location would be that one. So I add this length with this length. Due to the P2 is this line. So add this line, and that line. That gives you the total stress due to the application of all of those lines. Similarly, if a distributed load is applied, It's similar to this concentrated load. Individually, I can break it down, each element, assume one single concentrated load, applied at different location. So I add this length, this length, this length, this length, this length, and so forth. That would be giving the stress only at the location. So that's the way we can calculate the stress distribution under the different loading conditions. Let me clear the picture. We come back to that diagram again. But let us solve another problem. We solve concentrated load applied on the surface in a vertical direction. What about if a shear force is applied at point O on that infinite plane? The solution would be identical to the case that we studied before. The only difference is that I can use the same equation, right? That's all the point that we want to make. If the load is applied like this or like this, it is the same solution. The only difference is that in this case, angle theta is measured from vertical line. In this case, angle theta is measured from the horizontal line. So the angles will be different. Definition of the polar angle would be different, but the equation would be the same. In a similar fashion that we did, we can see that if the stresses are defined in that fashion, with that angle theta considered, integrating all these stresses on that circular path will give the shear force P as we expect. Now, what about if a concentrated force is applied at point O at certain angle, not horizontal, not vertical? Obviously, I can add up those two solutions that we derived before. But remember, theta here in that solution and theta in the previous solution with the vertical line would not be the same. So we adjust it accordingly. If the angle of the force is alpha, the equation here is adjusted, and this would represent the sigma r, theta plus alpha. That would be the case. So we have the solution for concentrated load, where the load is applied vertical, horizontal, or at any angle. It took probably many years for initial researchers to arrive at this solution. But the solution now seems reasonable and simple to work out. Once the stresses in these cases are defined, our next step is to calculate displacement. What is the displacement? And that is the same technique we use for every problem. Stresses are calculated. I know sigma r. I know sigma theta. I know tau r theta for the case of concentrated load P applied on that surface. I want to calculate displacement U and V. based on the knowledge that we have on the stresses. The first step, we use the Hooke's law. With the Hooke's law, we calculate epsilon r, epsilon theta, and gamma r theta. Which is 1 over E sigma r minus nu sigma theta, that gives epsilon r. Sigma theta minus nu sigma r over E sigma theta. And gamma r theta is my shear strain. Because the solution we provided showed that tau r theta is 0, gamma r theta should be also 0. Now, I know u, derivative of u with respect to r is epsilon r. Substitute for sigma r, sigma theta, which was 0, and then integrate it. Integrate that equation, you get u. From this one, the equation for the epsilon theta is given by this expression in terms of u and v. And epsilon theta is calculated by this equation. And this expression shows that this is 0. So we have 3 equations. First equation, second equation, third equation. From the first equation, we integrate the expression, we get u, and the constant of integration is f theta. Then look into the second equation, or the third equation here, derivative of u with respect to theta over r, derivative of that expression with respect to theta over r will be obtained by that equation. You get the derivative of this term with r plus derivative of f prime with respect to theta over r. We came to the end of the session. Time passes too quickly. I would like you to look into this chart. It would guide you through any other similar problems. You get V as well by looking into that term. Derivative of V with respect to theta is given. So if you integrate it and substitute into that equation, you get V. Substitute U and V that you have here into the third equation, and you get some relationship between Fr and F theta that should be valid for every value of theta and r. So that to be possible, each term which has r should be 0, each term which has theta, some of those should be 0. From there, you can see F is equal to CR, and F theta is given by this function of theta. It has constants C and A and B. We can get those constants A, B, C by looking into the boundary condition. The boundary condition on the top surface, because of symmetry, on the top surface here, because of symmetry, I should have no displacement V in this direction. This is the load that's applied, and in radial direction, this is the U, and this is the V. I cannot have V direction. The surface cannot move up here or up in the other direction, because otherwise I lose the signal. So at theta equal to 0, which is this direction also, I should have no motion in this direction or that direction. We get A and C is equal to 0. And the third equation comes when we assume somewhere at the depth D here, a long distance depth D here, the point is fixed. So this semi-infinite plate cannot move up and down. So the constant B will be calculated based on that. We come and discuss the solution here probably next week. We have a better time to talk about that, but for the time being, let us stop here and work on the homework problems of this week, which is due on Tuesday next week. And on Tuesday, you will be exposed to a certain number of homework problems that I consider them as your midterm exam 2. And the grading of that will go to the grading of your midterm exam. It is not only graded based on the effort you do, but it's also based on the correctness of the solution. All right.
Professor,
Yes.
yeah, I just have a question. I'm confused. Is it the number 8 or 9, the one for the exam?
I let you know on Tuesday. I don't remember what is the number at this time.
Okay, because
So I
next
have to
week
look at-
homework, the homework due next week is homework 8.
The first sets of the problem that you do on these chapters of curvilinear stress or the polar stress coordinate system, the first thing that you do on that is consider your homework. The second one that comes is assuming that you learned some concepts here, it would be on your exam.
Okay.
All right,
Are you talking about second midterm, or are you talking about the final?
second midterm.
Oh, so we have 2 midterms in this class and a final?
Yeah,
Oh, I thought we just had 1 midterm and a final, because I was looking at the syllabus and
I
there's
would
only
like
one
to
midterm.
distribute. I would like to distribute the load here, and every exam at this time that we will have would take this shape. Even the final one would be in this form that I give you the problem and you work on it during few days and giving the solution, because otherwise it's not that easy to give any of this problem and you work it out in an hour or so.
Yeah, okay, makes sense. Thank
Okay.
you.
Okay, take care. Bye.
Bye.